Hello, we would like to present our second phase of our data warehousing project. It's dedicated to data quality assessment, correction plans, data staging and creation of reconciled database, and finally loading data warehouse. We would like to start from architecture in our project. We adopt a three-stage ETL process. Our process starts from the analysis of data quality of our 5 sources in different formats. Then, after normalization, cleaning, transformation, and pre-integration of data, we build a reconciled database, which is later used to build a data warehouse. Now let's move on to data quality assessment. We are going to integrate several sources: Million Song dataset, Music Brains dataset, Yahoo dataset, and 2 datasets from Last.fm. For each of them, we made an extensive analysis with help of following tools like Data Cleaner and Data Quality Analyzer. We classified our problems in several classes according to quality dimensions. Accuracy. We are going to check if there are any value errors like outliers among age data, standardization errors, or precision, format and quality of timestamp, for instance. Completeness. Null value statistics is important for us in order to manage data integration process. Consistency. In order to have meaningful reports, we establish some domain integrity. For example, age of users from 5 to 100. Uniqueness. Awareness of existing data duplication is crucial for integration processes. We will start our data quality analysis with Last.fm datasets. First dataset is user recommendation Last.fm dataset. There are 2 tables. First table is user ID profile. It contains information about users in following format. Using data quality tools, we found that all values of user ID are unique. The gender field is normalized, but approximately 9% of records have null values, so there is a completeness problem. For age, amount of null values is significant, around 20%. Moreover, we have some accuracy problem with age. For example, there is some users with negative value of age. This amount is insignificant, less than 1%. There are also some values that are out of domain, with age equal 1002 or 121. Country does not have null values. User had only the option to select country from a list, so there is no chance that incorrect data appears. To summarize, this dataset has problems only with gender and age fields. The second table is dataset user rated plays. It provides the number of times an artist was listened by a user. The schema is the following. During the analysis process, we observed that all values of user ID are unique. There are approximately 2% missing values of external artist ID. Place. All values are in our domain. They are all positive values. There are only 2 outliers like 0 or 0.6. This number is insignificant. So, the correction plan is following. We should eliminate tuples with the outliers values, consider them as unknown values. Complete missing values artist ID by matching by artist name with external source. The next Last.fm dataset represents the whole listening habits of nearly 1,000 of users. There are 2 tables. First table contains information about users as in the previous one. Using data quality analyzer, we get the following statistic. User IDs are unique. For gender, we have just 10% of missing values. For age, amount of null values is significant, is around 70%. There are also some values of out of domain, less than 7 and greater than 100. Country is formalized, but approximately 9% of missing values. Registered date is also formalized and has only 8 missing values. So there are mostly completeness problem with gender, age and country. Second table contains information about user, artist ID, track ID and timestamp song was listened. Second table contains information about user ID, timestamp, artist ID and track ID. During analysis, we found out that there are around 3% of missing values for external artist ID and around 11% of missing values for external song ID. As a correction plan, we are going to complete missing values of artist ID and song ID by matching with external sources if it's possible. Next source is a Last.fm database about song text and similarities. The first dataset is text dataset. It contains three tables: text, all values in the field tag are unique but not normalized as you may see; tracks, all tracks IDs are distinct and unique; and pairs, tracks, tag and tag occurrence, no problem detected in this field. Problem of this dataset is the fact that tags are not normalized. We will use techniques like soundex to find the similar tags and eliminate them. The second dataset is the Last.fm song similarity dataset. During the analysis process, we didn't find any data quality problems, so this dataset does not require any corrections. Next dataset is in Music Brains. As you might see, this database has impressive structure and it's big to analyze. For our project, we made analysis of the following tables. In table area, we found a lot of duplicates, like City Paris has 6 different corresponding IDs. In artist table, names are unique on almost 91%. There are around 6% of duplicates. Artist names can contain illegal values due to specific nature of data. Around 50% of recordings names are unique. Recording names contain illegal values. Name entities are in their original language. Around 60% of release names are unique. Release names contain illegal values. Name entities are in original language. In the table release country, we found some problems with year field, like unidentified values, /n are 3% of all records. As a correction plan, we propose to eliminate duplicates in table area by choosing one out of duplicates and updating corresponding IDs, and replace values out of domain by unknown values. Yahoo dataset consists of two files. The first file contains user ratings of artists. We found problems with ratings. Around 30% of records are equal to 0. The second table contains artist IDs and names. Artist ID, all values are unique to values out of domain. Name, there are no null values. We propose following to exclude records that are out of domain. The last data source is 1 million song database. During the analysis, we found the following problems. There is a significant amount of duplicates in artist name field. For example, there is several ways of writing of duet of Ike and Tina Turner. Another problem that danceability and energy are not unique. All values are equal to 0. And there is a lot of negative values in the song hotness field, around 50%. So correction plan is follows: to trim illegal values, to replace by unknown values, and do not use meaningless danceability and energy.
Now I would like to tell you about our data staging process and the creation of our reconciled database. As data integration and ETL tool, we have chosen Talent, specifically Talent Platform for Big Data, because we were looking for a free, open source and cross-platform solution without any limitations in usage. After we got more familiar with data from integration point of view, we faced the need to make some changes to our DFM model. Firstly, we changed the relationship between song and release to many-to-many. We are not dealing with Music Brains tracks. Our dimension song is on a higher level of abstraction. That's why all the releases of all the tracks of Music Brain recordings are now connected to our song dimension. For the similar reason, we had to add many-to-many relationship between releases and mediums. Next, we joined Yahoo and Last.fm users into one table. Country is now connected with 3 fact tables directly. We deleted danceability and energy from song properties fact table because during the data quality analysis we found that these values are all zeros. We joined Yahoo and Last.fm users into one table. Labels now have location hierarchy starting from city level. Country is now connected with 3 fact tables directly. We deleted danceability and energy from song properties fact table because during the data quality analysis we found that these values are all zeros. We also deleted time signature from song properties fact table and added it as a dimension to song. It has only 7 discrete values and is more interesting as a dimension than as a value to aggregate. And finally, we have splitted the table song statistics into 2 separate fact tables, song features and song ratings, as they represent different concepts. So, with help of Talent, we started to create reconcile database. After exploring data, we highlighted some problems we want to solve by creating reconciled layer. During the data staging phase, we had several problems we tried to solve. The first one was matching songs from Million Song database and recordings from Music Brains. First of all 280 gigabytes of H5 files from Million Song database were converted to SQLite database, which was much smaller and was less than 1 gigabyte. One track from Million Song database should correspond to exactly one recording from Music Brains. At the beginning, we know that Million Song database uses artist ID from Music Brains, but songs are not matched between one another. So we selected all Music Brains recordings of artists from Million Song database. This set of records from Music Brains we tried to match with Million Song database recordings during several iterations. First, we tried to go with exact match, matching by song name, artist GID, song length, release name, and year. On the next iteration, we tried to soften our conditions a little bit and repeated the same procedure with, for example, name and year and release. Then we softened them again and repeated the procedure with name and year or release and length, and so on. Additionally, we repeated our procedure of exact match and soft match, applying some modification on source data, like lowercasing all the titles from MSD, using procedures to trim excessive spaces and symbols, using regular expressions, etc. As a result, we got a table of pairs which matched Music Brains recordings with Million Song tracks. We managed to match 53% of data, which is 532,000 records. For those tracks which didn't find their corresponding recordings on the previous step, we had to at least find a releases for them. So, to solve this problem, we applied the same approach with several iterations, started with exact matching and softened conditions step by step. As a result, we got the table with correspondence of Million Song tracks with Music Brains releases ID. We matched additional 18% of data, which is 187,000 records. Another problem was raw data of song similarities. The data was presented in this way. One track had a set of values delimited by commas which were not parsed. We used the JavaFlex component to handle this problem. As a result, we got a table of the following format. One track had one track ID and the value of correspondence. The area table in Music Brains is not normalized. That means that all geography types are in one table. Cities, countries, continents. A lot of entities are referencing areas from table, and we cannot tell which type of geography they are using. In our data warehouse, the geography information is hierarchical, so we had to build the hierarchies out of existing data. For this aim, we used the world cities population file and the previously mentioned tricks to match the names of geographies from Music Brains, like trimming, lowercasting, etc. The next problem we faced was the problem of partially known values for geographies and dates. For example, due to the already described unnormalized area information in Music Brains, some of the labels in this dataset have city information, some have only country. As we didn't want to lose such important information as city of the label by simply rolling it up to the country, we created for each country the unknown city, for each continent the unknown country, and etc. So now when we know for the label only the country, we connect it to the unknown city for that country. As you know, initially we didn't have any source for the ratings for our songs, but we decided that this is very important information which will make our data warehouse more versatile. Music Brains provides REST API which can be queried to get the rating for the particular recording. We wrote a script to get the ratings for all our recordings, but unfortunately the API allows a limited amount of queries per second, and so far we retrieved ratings for a very limited number of recordings. After a closer look at Music Brains data source, we figured that one release is actually in many-to-many relation with country. That means one release could be produced in several different countries. In order not to make the rollup to country complicated, we decided to make country a dimension of our release statistics fact. This entailed, however, adding the same country dimension for song features and song ratings facts, as we do not want to lose an opportunity to aggregate these values by country. This means that for each combination of song, country, date, we will have the same rating and rating count values in effect song ratings. But when aggregating to continent, for example, all the rating counts will sum up, producing incorrect amount of rating counts. We decided to fix this problem by adding another field, weight, which is actually 1 divided by the amount of countries this song was released at.
Finally, we reached the step of loading our data warehouse. After the initial data integration process on our reconciled database, we have the following additional tables like IDs of matched tracks from Music Brains and Million Song database, matching between Million Song database tracks and Music Brains releases, hierarchical geography tables and their matching with Music Brains geographies, already joined Yahoo dataset, Million Song database, and etc. This reconciled database simplifies many of our loading process. The only problem we faced on this stage was with the huge amounts of data we had to operate on. Sometimes the amount of records and tables reached 100 million. Very often our computers couldn't process all data at once, so we had to partition it and process part by part. Now we would like to present ETL execution plan to load our data warehouse. If you want to have a closer look, don't hesitate to check attached presentation. Initially, we started to load our data warehouse from peripheral dimensions like users, locations, dates, tags. Second wave of processes was to load dependent dimensions of artists and labels. On the third step, we load two fact tables, artist place and artist statistic, and several bridge tables. Subsequently, we were able to load release dimension, what was the turning point. After loaded releases, process continued with loading release statistics fact table, song, and medium dimensions. Finally, we reached loading remaining 4 fact tables. Because of great preparation work on the reconciliation step, we didn't experience overcomplicated loading process, but we would like to show a few illustrations of our ETL. For instance, process of release dimension loading. For those tracks we couldn't find corresponding release for, we create the release artificially by taking the release name and release year from Million Song database. So the upper branch is creating these artificial releases with name and year of the track. The lower branch is doing routine lookups, and the last tmap component is dealing with the null values, substituting them with special unknown values. Finally, we merge the branches and save the result. Another interesting process is the process of moving the connection between songs and releases. To create correct song release connections, we have to consider 3 inputs. First, the tracks from Million Song database, for which we couldn't find the corresponding releases among those from Music Brains. We joined them with our artificially created releases. Second, those for which the release was found. Third, the recordings directly from Music Brains. Again, all necessary lookups are done, inputs are merged and loaded into data warehouse. So, here is the final logical schema of our data warehouse. If you want to take a closer look at this DFM model and the logical schema, we attach them to a video. So, we hope that you now have a clear idea how we managed to load our data warehouse. Following numbers might help you to imagine complexity of our project. Thanks for your attention.